Good afternoon, ladies and gentlemen. We are now going to start the next portion of geometric optics, which is about thin lenses. Now, lenses are different than mirrors because mirrors were based upon the idea of reflection about the normal line. But lenses doesn't deal with reflection. It's entirely about refraction, about light actually traveling through the lens itself and bending when it goes through. So it's not about reflection. And because it's not about reflection, we're going to see that the material of the lens will actually have an effect on the image that's being formed. The shape isn't just the only thing that's important. It's also about the type of material, or in other words, the index of refraction. Well, let's go back to this picture for a moment. There are two main types of lenses: converging lenses and diverging lenses. The first set, these are converging lenses. The main thing that distinguishes what a converging lens is that it is thicker in the middle and thinner around the edges, as you can see through all of those examples. The most obvious example of a converging lens, of course, is a magnifying glass. And we're going to talk about the kind of image that's being formed by the magnifying glass later on. So let's just write that down. The example is a magnifying glass. The other type of lens that we're going to be talking about is what we call a diverging lens. So if I just raise this picture up a little bit over here so we can see, you can see a diverging lens is the exact opposite of a converging lens. For basically, a diverging lens is thinner in the middle and thicker around the edges. And the most obvious example would actually be the glasses that I'm wearing right over here. These are actually diverging lenses. And if you look at the side of the lens itself, you'll see how the lens has a thicker portion near the edge where the frame is. And in the middle, you actually have a thinner portion. So it's actually very similar to this last example over here, where it's thinner in the middle, thicker in the edge. Okay, that's a diverging lens. And of course, the words converging and diverging automatically make you think about what's happening to the light. Just with mirrors, where they had a concave mirror with a converging mirror, and a convex mirror with a diverging mirror. So with a lens, okay, a converging lens basically has the parallel rays of light going through, and they all bend so that way they all converge together. As we can see, they converge through what we call, again, our main focal point. Okay, but you have to realize this is different than a mirror in that a mirror, when the parallel rays of light struck the mirror, they reflected back. And the focal point was on the same side as where the rays came from. Now the rays of light are actually going through. Okay. So with a diverging lens, we can see that when the parallel rays of light strike the diverging lens, they do diverge and separate from each other as they're going through the lens. And they're not going to come together at all on the real side, but rather they're going to come together on the virtual side. So if we bring those lines back, we can see that there's a virtual focal point for a diverging lens. Okay, and the virtual focal point is, of course, not really there, but it's what we're going to use for our calculations. Now, A converging lens, I want you guys to realize, doesn't even have to be glass. It doesn't have to be plastic. It could even be something as simple as a water bottle. If you just watch this demonstration of what happens when you use the sun and use your water bottle to focus the rays of the sun to light a fire.
Normally, we'd think of using water to put out a fire, but in this video, you'll learn how to use water to start them. The black ink is showing, and that's a good thing, so now we can prepare these other two sheets by cutting or ripping them in half. This gives us 4 pieces, and we can fold each of them in half so that they're creased down the middle. Alright, time for the action. We'll need to remove the label from this little bottle and use the convex edge as a makeshift magnifying glass to focus the sunlight. It only takes a few seconds to get this paper smoking, and pretty soon, we've got it smoldering. When the hole is about the size of a quarter, we'll need to slowly add multiple layers of papers. Swinging it around gently will help the air get to the embers, and when they get hot enough, a flame appears. That's it in a nutshell, but in practice you'll probably find that it's not quite as easy as it looks. So here are a few tips and tricks to help you.
Okay, so basically the round shape of the water bottle is a converging lens. It's thicker in the middle, it's thinner on the edge, and so ultimately it's able to focus the rays of the sun at the focal point. So when we actually do this mathematically, we have to be careful with how we draw this, okay? For the most part, it's almost very, very similar to how we draw mirrors, but there's a few key differences. First of all, when you're starting your drawing, I want you guys to always draw a line straight down the middle of the lens. Well, as straight as you can, at least. And understand that when light does travel through, there is going to be focusing through some sort of, focal point. But rather than writing C, like we did for mirrors, we're going to write simply 2F. So it's still equidistant. If this is F, 2F will be equidistant from F to the lens and F to 2F. Now, the reason we write 2F and not C is because it's not necessarily going to form a circular shape anymore. It's about the material of the lens itself that chooses where the focal point is going to be. For example, if I use something with a higher index of refraction, so I'll write if N is increased. That means before, when the ray of light came across, it will converge through the focal point. But if I send green light through, which has a higher focal point, higher index of refraction than red, it's actually going to bend more. So in this case, it will look like this. And F for green would be over here, and 2F would be approximately over here. So that's part of the reason why I don't actually write down F and C. I'm going to use F and 2F, because it changes entirely based on what the index of refraction is. Okay. So again, line straight down the middle, F, 2F. Now the thing is, the lens is curved on both sides, so on the other side, I'm just going to write F prime and 2F prime. Now, they're basically going to be our our secondary focal points. We're not really going to be using it, but if light were to travel from the other direction, it would travel through to F. And it's going to be important to us when we actually start doing ray tracing. Okay. Now, if we go to the diverging lens, the diverging lens is the same thing, where we have a line straight down the middle. But now remember, when light travels and hits a diverging lens, they all diverge outward. So our main focal point is not going to be on the right side. Instead, the main focal point is going to be on the left side. So since the main focal point is going to be on the left side, I'm going to label F over there. And 2F will, of course, be equidistant, while on the other side, we'll have F prime, 2F prime. Okay, so let's keep that in mind for once we start doing ray tracing. Okay. Just like before, we're going to follow certain rules about how we draw the lines. And the rules for lenses are almost the same as mirrors. Okay? The rules for ray tracing lines are, we first go parallel along the axis. And after it strikes the lens, it's going to go through F. Notice I said F, not F prime. It goes to the main primary focal point. The second line is through F prime, not F, it's through F prime, then parallel along the axis. So technically that's always going to be our second line, but in reality it's a little bit hard to draw, and I know that you guys tend to be a little bit messy. So we're going to skip the second line. We're always going to jump to our third line, our check line. The third line is the easiest one. All it is, draw a line straight through the center of the lens. Okay? Because when you hit the center of the lens, and if you take a look at a third drawing here, when it hits the center of the lens, technically it's striking exactly on the normal line. And whenever you hit exactly on the normal line, just like in refraction, it goes straight through. So in this case, it would actually go straight through for our image formation. Okay? So let's try this out a little bit and take a look at a few different examples. The first example we're going to deal with is the magnifying glass. Okay? So the magnifying glass is our converging lens, but you have to be careful about where the object is versus where the image is. Okay? If you take a look at the magnifying glass itself, okay, you'll notice depending on where the object is. So right now, let's use me as the object. Okay, you guys are looking at me. So when it's up close to me, when I'm very up close, you guys, if you're taking a look at my eye, I'm sure my eye looks enlarged. But when the magnifying glass is further away from the object, and if you guys are looking at my face now, you should see that my face actually appears upside down in the lens. And this is a real image that's being generated by the lens itself. And this is going to you, to your eye over there. So let's just do a little bit of ray tracing and see what happens. Okay. Let's first actually do where we hold the object further away from the lens itself. Okay, so that's this example over here. Now, a few things to note, and we'll need this for mathematical purposes as well. Okay, which side is real, which side is virtual? Just like before, real means inverted, virtual means upright, but you have to keep in mind where is the eye. So right now, if this is the arrow on the left over here, I want you guys to take note. That means you guys are looking through the magnifying glass in the middle at the object. So just like when you guys are looking at me, right? You see that I'm upside down. I probably appear smaller than my actual size. So that is what your drawing should look like as well, and it's what it should indicate. So if I label this as F and 2F, I know that the right side, wherever the eye is, that's always your real side, and the other side is going to be my virtual side. So I have F prime and 2F prime. I follow my basic rules, parallels in through F, so parallel, then through F. My second, I could do through F prime and then parallel, but it's just easier just to always do it straight through the center. So just line up your ruler with the center of the lens, and just draw it going straight through. And wherever the lines converge, that's where the image is. So over here, I have a real and smaller image. And notice, since it's smaller, the distance of the image from the lens is smaller than the distance of the object. Because if you remember, the magnification is directly proportional to how far away it is from the lens also. So we actually have a smaller real image. And that's what you guys see when you're looking at me. If you take a look at the next example, you'll notice this object is on 2F prime. Now, I want you guys to be drawing in the eye as well, because it's good practice and it'll help you guys for the math. If you remember with with mirrors, with a concave mirror, when the object was on C, where was the image? Well, we'll see over here, parallel, then through F, through the center, the image is exactly on 2F. So because the distance of the object and distance of the image are exactly the same, we know that it's going to be the same size. Okay? Now, one more example. Okay. Now, this is interesting because you're actually looking at this example right now. You just don't realize it. We have an object that's now closer to F prime than before. And if you remember with concave mirrors, the closer the object was to the focal point, the larger the image appeared. And the same is exactly true for lenses. The closer it is to F prime, the larger the image appears. And this will work out the same way. But let me just draw my eye. Positive, negative. Okay. Parallel, then through F, straight through the center. And you can see my image all the way over here. It's real and it's larger. Okay, and you guys might be thinking, what does it actually mean that it's real and it's larger? Well, the image is actually there. When you look at the smartboard projector, any projector system, if I were just to sketch this out for you guys, okay, normally there's some sort of projector with a lens, okay, and there's a screen over here, and on the screen you have the image being projected onto a screen, let's say of a tree or something. What's inside your LCD projector is an actual little mini LCD screen, meaning that inside there's a picture of a screen with a tree on it. But of course, because every real image becomes inverted, they actually start this image upside down. So there's a little tree that's upside down that's then projected through the lens onto the screen. And the screen is exactly the distance of the image. And the distance of the object would simply be from the little miniature LCD screen to the lens. And this would be, if you were to actually draw this out as a real lens, the object will be between F prime and 2F prime. In fact, let's show you guys a quick video on this. Let me erase this. Okay. Now in this YouTube video, the person in this video, okay. So in this video, the person is actually making his own homemade projector using an iPhone and a magnifying glass. He's putting the magnifying glass and turns it away and cuts it out. Okay, let's just turn off the music. And he puts his phone inside. He turns the brightness all the way up as much as possible. He makes sure that his phone is in between the focal point, F prime, and 2F prime. And when he uses it, he will actually project an image onto the wall behind the projector. So if we take a quick look at the end of this video clip, it's not going to be very bright because honestly an iPhone isn't very bright. But I'll just pause it right here. You can see that there's an actual image being projected over here. Okay? But that image, if you were to take a look at his phone, is upside down what his phone is actually doing right now, because it's a real inverted image. I know it's a little hard to see, but hopefully you guys see that basically it's a real image. This last example over here, well, these last two examples over here, are again similar to concave mirrors. F, 2F. What happens when an object is placed on 2F prime? Well, just like with concave mirrors, when an object is placed on F, hold on, let me draw my eye because it's a good habit. Parallel, then through F, straight through the center. Are those two lines ever going to meet? No, they're completely parallel to each other. So in this case, it's going to be no image, just like with the concave mirror. Okay. And the last example is about holding a magnifying glass up close to something so that the object is actually in between the lens and the focal point itself, just like my eye is right now. So, just like with a concave mirror, which is like a makeup mirror, when you're held up close to something, you're going to create a magnified image. And as you guys could see, it was virtual and it was larger than before. So, let me draw the eye, positive, negative. Okay. Parallel, center F. Oh, that's a terrible line. Let me just redo that one. Then through the center. Okay. Now they're diverging apart, meaning that they're never going to meet on the real side. So we'll backtrack them a little bit. And there's the image, a virtual image. So this isn't something that's being projected through the lens, as in the case of the projector. This is something you can only see within the lens itself because it's an illusion that the mind makes up to create this virtual image. So this is going to be virtual and larger. Okay. Now let's talk about diverging lenses. Okay. A diverging lens is similar to a convex mirror or a security mirror. So if you take a look at my glasses at my face, right? Hopefully you guys can see what kind of image is being produced. And hopefully you can see that I'm upright, which means that's virtual, and that the image is smaller than before. Again, just like a convex mirror or a security mirror. So in this case over here, when you have the eye on the right-hand side, look at the object, you see a virtual smaller image. So let's actually trace this out. Let's trace it out first, then we'll talk about the example. line down the middle. Now remember, light diverges when it hits a diverging lens, meaning that it's going to bend away. So that means this is my main focal point on the left. Even though my eye is still over here on the right-hand side, and this is positive and this is negative, my main focal point is on the virtual side, meaning that it's a negative value. F prime will be on the other side. Of course, there's also 2F and 2F prime, but they're not really that important in this case. That's because I want you guys to see we have our first line, parallel, diverges, then back through F. And then the second line is straight through the center. And where those lines meet, that's where we have our image, which is right over there. Okay, so we have a virtual, smaller image, and that is the only type of image that's being produced, just like with a convex mirror or a diverging mirror. So let's see. Let's take a quick look at some animations just to double check our work and to show you guys what's going on. Okay, over here I have a converging lens. You can see when the object is on 2F, or really 2F prime, that it's the same exact size. When you move the object closer and closer to F prime, the image gets larger and larger. If you go onto F prime, there's no image being formed because the rays are parallel to each other. And if you move between, just like with a magnifying glass, keep in mind the entire time the eye is over there. Okay? So because the eye is over there, you see a magnified larger image. And the closer the object is to F prime, the larger and larger the magnification is. In fact, it's so large, you wouldn't see the entire object. Because like when you're looking at my eye, you can't really see my entire face because it only magnifies a certain part to be much larger. When you have it much further back, okay, we have a real image being produced on the right-hand side. The farther away from F prime, the smaller the image, just like when you're looking at me through this lens over here. Okay, it's a smaller image that's upside down, which means it's real and it's inverted. If you take a look instead at, let's see, sorry, give me a moment, a diverging lens, I want you guys to realize the eye is over here, so this is positive, this is negative, and no matter where the object is, it's still going to always be a virtual smaller image. Okay, we're parallel through F straight through the center. So this one's very easy to draw. It's not as complicated as a converging lens because there's only one type of image produced. Because mathematically, you have to remember that this is a negative main focal point. Now, what else can we talk about in terms of an easy example to understand? And the best one, of course, is the human eye itself. So if we talk about the human eye, okay, I want you guys to realize the lens in your eye is a converging lens. But let's just actually play this video quickly.
Stets scharfe Bilder einzustellen.
Which is in German, but we're not going to worry about it too much. So normally when light strikes the eye, it converges, I'll pause it for a moment, onto the optic nerve, which is at the back of the eye. And so when you see a picture of a tree, it will actually show a little real image of a tree that's upside down behind the eye. Except that your eye, your brain, has been trained to take that image and flip it right side up, which is why we see everything upright. Even though technically we're seeing the images of being focused in an inverted way on the back of our eye, it's going to be right side up. Now, the thing is, if you happen to be nearsighted, okay, that means that the lens in your eye is either a little bit fatter or that your eyeball literally is slightly longer. But because it's slightly longer, the image focuses at the wrong location. And everything looks a little bit blurry because the image has to be projected onto the optic nerve exactly in order for that to work. So to fix that issue, I wear glasses. I myself am nearsighted, and let's see, hopefully, there we go. If we put a diverging lens in front of the eye, the light will actually diverge outward first before converging exactly onto the optic nerve. That's how glasses work. That's how my glasses work for someone who has myopia. In other words, I am nearsighted. For someone who happens to be farsighted, the image is actually projected behind the eye. So to fix that, they're actually going to put a converging lens in front of the eyeball, which brings the light together, so that way it'll focus directly onto the optic nerve.